Now the overlapping of p orbitals, electrons in p orbitals, will result in the same phenomenon. Constructive interference will produce bonding orbitals, and destructive interference will create antibonding orbitals. We can indicate that as if they produce sigma bond, 2p, one without the asterisk for the bonding orbital, one with the asterisk for the antibonding orbital. You can also see that if there are unhybridized orbitals that overlap off-axis and for double bonds, of course these are going to create pi bonds. And so what occurs here is we can indicate that these are pi bonds with our simple indication, but of course there are going to be constructive interference from that pi bond overlap, bonding orbitals, and antibonding orbitals. You can construct molecular orbital diagrams for simple diatomic molecules that will utilize p orbitals, and again they are going to overlap to create both bonding orbitals and antibonding orbitals. And depending on the constructive interference, that will either lower their energy. So it turns out in this case, the pi 2p bonding orbitals are the lowest energy. That's why we'd write them on the bottom like this. Now you can fill out the electrons in these molecular orbital diagrams, like we did here. Then calculate the bond order of these molecules and show whether or not we would predict stable molecules or not. So here we have oxygen with a bond order of 2, fluorine with a bond order of 1, and neon 2 with a bond order of 0. There are more electrons too many electrons in the antibonding order. This raises their energy and of course does not predict a stable molecule. Now this bonding theory, molecular orbital theory, has its place in a lot of different types of chemistry, and one of the first examples where we'll see a example where molecular orbital theory is the best explanation for bonding theory is the fact that oxygen, O2, is paramagnetic. Now remember that paramagnetic implies that there have to be electrons that are not paired. Now if we take a look at Lewis structure, our first theory, we don't see any information that would give us the belief that the electrons would be unpaired. Anytime we show a Lewis dot structure, we always pair the electrons. If we look at valence electron theory, we see that all of the electrons are overlapping, therefore giving them spin pair, and if the spins are paired, we know that they are going to cancel out and not be attracted to an external magnet. Only when we incorporate molecular orbital theory and see that 2 of the electrons are in the antibonding pi orbital and that they are occupy that position in an unpaired state, do we see that oxygen is paramagnetic. And you can see the absolute proof of that in that we're pouring liquid oxygen in between 2 very strong magnets, and because oxygen has those 2 unpaired electrons, it is attracted to an external magnetic field, and you can see that the liquid oxygen is building up or just floating in between there, attracted to that magnetic field. Molecular orbital theory is the only theory that shows and explains why that is the case. So here we can see graphical representations of Lewis structures for ozone and valence bond theory. Molecular orbital theory is another really good way to show the fact that we know that those electrons are in resonance. They actually go back and forth that we saw in Lewis dot structure, and here we can see how they go about being shared across the ozone molecule. The same thing is true for benzene, which has an aromatic rings of electrons that are delocalized around the pi bonds above and below the aromatic ring.